Okay. Hello. Good morning. Nobody's here yet, at least not in spirit. So I would like to remind you all to please use the Scala Days app to rate the sessions. Of course, this session is the best one. You should assign it the highest rating possible. Leo Tolstoy, noted database theoretician, writes, "All happy databases are alike. Each unhappy database is unhappy in its own way." This, of course, from his seminal paper, Concurrenina. I would like to talk to you today about some of the ways in which databases become unhappy in the hopes that we can learn a little bit about how to make them better. My name is Kyle Kingsbury. You might know me as Afer online, and I have the worst luck with computer systems. For whatever reason, like laundry machines break when I put coins into them. I got stuck in a parking garage because of a concurrency bug that insisted the car was already outside the garage. I have problems filing my taxes because the state insists I both have and have not paid. Concurrency bugs rule my life. And I've been trying to make the best of this by understanding how concurrency problems manifest in practice for computer systems. Computer systems like APIs, like production services. You know, we think about APIs as being like a beautiful rainbow in the sky, right? It's an abstraction that our customers love to behold. They look at the gorgeous rainbow and they say, "Oh, what a wonderful service you provided to us." What they don't know is that that service, that rainbow, is supported by physical infrastructure, by this code that you wrote in these brittle girders, the tower abstraction that stretches all the way down to the VM, to the JVM, to the Ruby VM, to the Go runtime. It's those wooden pilings that sit underneath our beautiful abstraction code slowly rotting away. And that wooden piling is in turn driven into a firm foundation of databases and open source persistent systems that we found lying around on the internet, represented here by a pile of tires. Now, as anybody who has worked with the database knows, the pile of tires is usually on fire. And it's our job as good engineers to engage in a practice we like to call information hiding. We don't want anybody to notice that there's a fire going on inside the company while users are making requests to our API service. So we're gonna build the tower abstraction higher and higher in an effort to climb away from the awful flames that consume us all. We call this infrastructure reactive. Now, I'm not just talking about databases here. I'm thinking about queues, discovery services. All of these things strike fear into the hearts of engineers. Why? Well, because they do terrible, terrible things. They get into split brain, where two sides of a network believe different truths. They get into situations with this broken foreign key constraints. You go to look up a record and it's not there. Or maybe you have transient anomalies where you write something and then go to check it and it's not there yet. And you refresh the page and now suddenly it's come back. What happened? I'm trying to figure out, do these anomalies manifest in our software? And if so, why? How can we even tell? The only way to figure that out is to measure for ourselves. We actually have to go and look at the system. We have to slam those cars into each other and film with high motion cameras to see all the little bits and find out if our writes fly out of the window. It's a tortured metaphor, all right? So, Jepsen is a project to analyze distributed systems under stress and to understand if concurrency problems are going to manifest not only in our applications, but in databases and queues and so forth. Jepsen is a testing system which treats the world as split into two things. We have the environment, that's everything outside, that's our clients. And then there's the system itself, which is usually like some Linux machines running a network with some software on top of them, maybe a few services here and there. So that system is going to have lots of internal moving parts, but we're going to draw a boundary around it and pretend none of that complexity exists. Again, information hiding. But at that boundary, there should be some laws that hold. You know, good abstractions involve laws, right? Type systems are an abstraction which allows us to ignore the behavior of types, for example, division by zero. That the invariants that we care about in a distributed context are things like when you put something into a queue, it should come back out again. Or when I register a username, nobody else should be able to register that same username again. So we're going to check for those invariants by running a bunch of clients outside of a cluster. We'll have, say, 5 computers running a cluster of a database or a queue, and then we'll have clients making requests to and from it. And those nodes will communicate, and hopefully the system as a whole provides the illusion of a single coherent entity in some way. Now, we have no insight into what the database is actually doing. We're running arbitrary software that we got from the web, right? There's no code analysis, there's no visibility into it. It's just this opaque box that gives us some API to talk to. But what we do know is exactly what the clients did. We know every write, every read, every compare and set, every enqueue, every dequeue. So our clients will generate randomized operations like take out a lock or enqueue an item into this queue, and then we'll apply them to the system and then see how they've resulted. There's 3 ways that could turn out. It could either succeed, and that's where we know the operation took place. We'll record that as OK. Or it could fail, and we know it didn't take place. That's when we get like a constraint failure message, or maybe, sorry, you're out of disk space, you won't accept the write, or maybe the TCP connection couldn't open. Or we can have an indeterminate failure, and that's the worst type. That's where you get like a timeout or a crash or some other case, and we're not sure if it happened or not. So we have to consider that that operation could take place at any point for the entire history. Now, we're not just going to do this on one client. We're going to have several clients going concurrently. So each client will be invoking and completing, invoking and completing. If it crashes, we're going to leave it crash for all time, because it might take effect some later point. But since we'll have multiple clients running at the same time, we'll have a concurrent history. So that means there could be multiple enqueues and dequeues going on at the same time. And our job becomes to look at this history and identify, does it make logical sense? If I'm measuring a queue, does everything that I put into the queue come out at some point? If I'm making a linearizable register, can I find a path that goes through the system, always going forward in time, so that every successful operation must occur and every crashed operation may occur? If I'm making a serializable system, I can ignore the temporal order and just pick any ordering I like. Is there some legal order where the operations of the system make sense? So our general scheme here is to generate randomized operations, record a history of those operations as they're applied to the database, and then verify that history is consistent with some abstract model of the system. This is a generative testing approach like you'll see in QuickCheck or test.check. And while this is going on, we're going to go and get our bolt cutters and our giant pruning shears, and we're going to start cutting the network into bits. We're going to sneak into the database's houses at night and change their clocks around so they wake up at the wrong time. We're going to drop sleeping powder into their stew so maybe they forget to do a write at the right point in time. We're going to scribble on their calendars so that they go to the wrong child's PTA meeting. And hopefully, we'll be able to uncover anomalies in the database. The question is, how much do we have to interfere with their lives in order to watch them go mad? Like I said, unhappy databases. So, what have I found with this approach? I started doing this back in 2013. And I tested Riak, which had 2 known results. These were documented, already hopefully well-known properties of Riak. The default last write wins mode will lose writes because it only orders things by wall clock. The CRDTs, however, allow you to do safe commutative updates. MongoDB, on the other hand, lost data at every level of write concern. This is partly due to a bug which considered a network failure a successful response. Since fixed, Redis Sentinel would go into split brain and throw away all writes on one side of the partition. It would just clobber it when they came back together. Cassandra also had last write wins, write loss. There's no safe way to do an update in Cassandra. It also claimed to have row-level isolation, but that, of course, is a lie. It also claimed to have a transactional system which deadlocked, and when the deadlock bug was fixed, it would lose data by double applying transactions. It's hard to build Paxos. NuoDB claimed to beat the CAP theorem by buffering all requests in RAM during a partition. Reactive. Kafka, I'm sorry, I'll stop. Kafka, in its 08 beta, had a replication model which had an in-sync replica set, like the nodes that are considered to be up to date. And that set could shrink arbitrarily small, including just one node. So one node would be signing off, being like, yep, got your data, everything's fine here. And if that node fell over, all those acknowledged writes would be gone. Zookeeper actually passed, which I consider to be a personal failing. On my part. etcd and console both claim to offer you the most recent values of data, but in fact would give you stale data. We had a little bit of a debate over that, and they've since fixed it. Elasticsearch lost documents in every class of network partition we tested. RabbitMQ, like Redis Sentinel, RabbitMQ's documentation actually says should not be run on networks that may experience partitions, which is my favorite. I mean, it's a good queuing system, except that it happens to lose messages that are acknowledged if you run it with partitions. Aerospike claimed to be an ACID data store. Turned out it was last write wins, eventually consistent. It threw away data. I went back and tested Elasticsearch again at 1.5, and it still lost data in every test case, but this time it lost less. They've narrowed the windows. MongoDB 2.6.7 had fixed the lost writes problem that we had originally. But it still allowed two cases, one known, and that was dirty reads. You could read inconsistent data from the middle of a transaction. One that was not known is that you could have stale reads as well. You could read old versions of data after successful writes. Chronos, a distributed cron scheduler built on Mesos, would stop being a scheduler after losing quorum. So it would never run your tasks ever again, even if the network recovered. That was due to a bug in the multi-paxes implementation in Mesos. Percona XRDB and Galera Cluster in 2015 claimed to have snapshot isolation, but the snapshots weren't snapshots and weren't isolated. This is still, as far as I know, the case. RethinkDB, back in 2016, actually passed its test. It offers linearizable reads, writes, and compare and sets on a single document. However, we pushed a little harder, and we're able to find a bug where if you change the cluster membership during a partition, it could inadvertently delete all the data on one replica and then bring it back with the same name due to a startup message being delivered twice in rapid succession. This is really tricky to hit. But if you're doing a whole lot of changes really fast, you could force it to come back without any data, and then it would proceed to vote twice and maybe invalidate, well, basically everything. So, as Kitty says, be bad, but at least don't be a liar, a deceiver. I want to encourage database vendors to be accurate in their claims. It's okay if you lose data. It's okay if you don't offer strong consistency. But please tell your users about it so that we can make informed decisions. So I would like to talk to you about some of the research I've been doing recently, starting off with VoltDB at version 6.3. VoltDB is a really cool database. It's a distributed SQL store, scale out. It's called an in-memory database, but in fact that just means that it stores all of its data in RAM plus on disk. So it has a regular write-ahead log like you'd expect. It's not just in memory. It offers this usual family of SQL queries. But for transactions, instead of having like a begin and then a commit, instead you write like a store procedure in Java that builds up SQL statements, and then you ship that like class file off to VoltDB, and it will do some static analysis to try and figure out if it can safely execute it in certain optimized paths, which allows it to be a little bit faster for some classes of transactions. It's intended for high throughput, mostly sharded transactions. And the reason for this has to do with Volt's architecture. Like many databases, VoltDB splits up its key space into shards, which they call partitions. These are not to be confused with network partitions. They're a different thing. So maybe keys A through L go to one shard, M through Q go to a different one, R through Z to a third. And on each of those data partitions, there's what's called a single partition initiator, the SPI, whose job it is to act like a leader for that group of replicas. So the SPI takes every transaction that you want to apply to that group of keys, puts them into a total order, and executes them one at a time. And it will replicate them out in the same order to all of its followers. So everybody does the same operations in the same order, and therefore comes to the same state, assuming determinism. When you want to do a transaction across multiple partitions, you can't just talk to an SPI anymore, because it wouldn't give you any consistency guarantees across multiple partitions. So now we talk to a single global coordinator in the cluster called the multi-partition initiator. And that thing's job is to give a total order to every transaction that has to cross multiple partitions. What this implies is that transactions in a single partition are going to scale linearly. You add more partitions, you get more SPIs, you get more throughput. But transactions that cross partitions have a fixed throughput regardless of cluster size. And in fact, they'll get a little bit slower as you add more nodes because of coordination overhead. So the consistency claim in VoltDB is that all transactions are strict serializable. And to refresh your memory, strict serializability lies at the confluence of two hierarchies of consistency models. It is the conjunction of linearizability with serializability. Again, serializable, repeatable read committed, read uncommitted, those are the SQL style, multi-object transactional models. Causal, sequential, linearizable, those are like single register models for concurrency analysis. Strict serializable says not only do you have to be serializable so that every transaction takes place in some order, none of them can overlap with each other. So notice that here we've taken transactions from the top and bottom workers, and we've brought them together into the same timeline so that none of them overlap. None of these colors merge together. That means that the transactions appear to execute atomically, one at a time. But it's not necessarily the same order they were executed in. So here, one client performs green, then blue, but blue gets executed first and then green second. So there's no fixed order. Linearizability is a little bit stronger. It says you have to choose an order which is consistent with the real-time boundaries of the operation. So if I want to perform this green transaction here, I can't serialize it anywhere outside of this region when I make the call and when it finishes. I have to happen somewhere in this point. And that prevents us from getting into pathological orderings where you read from the past or write to the future. So strict serializability is a conjunction of those two things. It's a multi-object transaction which has that real-time guarantee. Now, VoltDB 6.3 unfortunately exhibits several violations of strict serializability, and they're really cool. So it has stale reads, it has dirty reads, it has lost updates, it's a floor wax and a dessert topping. Stale reads are cases where you, say, have a write of 0, and then you read 2, and then later read 4. Say, okay, well, when I read 2, the value has to be 2. So how can I read 4 later? Well, there would have to be some intervening write of 4. But in this case, there isn't one. I could change the value to 0, that's all right. But if I then try to read 4 and the current value is 0, it's going to fail, right? Because those aren't the same number. So this is an illegal history. And the reason has to do with a split in the network. Just prior to this occurring, these two nodes shared the same value of 2. But then a network partition separated them, and the bottom node, node 2, became a leader. That node can execute writes, so we can write 4, write 4, write 4, and we can read 4 back from that new node, but the original node, node 1, doesn't know about that update, and it will continue to service reads. So you could read 2, 4, 2, 4, 2, 4, as long as both nodes are going. Now, I said earlier that for a single partition, the single partition initiator orders updates, right? So how could we possibly have this unordered process? The reason is that writes are ordered, but reads aren't. Read-only transactions bypass the single partition initiator for performance reasons. They just execute immediately, which is serializable, but not strict serializable because it lets you read from the past. You can read from isolated nodes while the other nodes have moved on to new values. The solution is fairly simple. We just push everything through the single partition initiator, so you can no longer apply that optimization. Dirty reads is a little more subtle. This is a case where you perform a write of a record, say you write 3, then abort, and somebody else manages to read 3. Imagine you're making a sandwich. You got your bread and your peanut butter. You start putting the peanut butter on the bread. And you're like, yeah, it's going to be the best sandwich ever. And your little sister comes into the kitchen. It's like, oh, you're making sandwiches. She runs off and tells your brother, like, hey, come on, he's making sandwiches. Come get some. And you realize that you have no jelly. Like, well, shoot, I got to abort. So you remove the peanut butter from the bread and you put it back in the container. And you nicely package up everything. You put it back in the shelves. You say, okay, no sandwiches today. You abort the commit, right? Then your sister shows up with your brother, like, hey, we heard about sandwiches already. Did you make them? Like, no, there were never any sandwiches here. How did you find out about this, right? This is this is a dirty read, okay? So this is not supposed to happen because when transaction 1 is written to node N1, our primary, it's going to commit locally. It'll be replicated out to N2 and N3. They'll commit locally and they'll acknowledge. And when everybody's acknowledged, we return to the client and say, okay, you're good to go. However, if there's a partition between N1 and N2, that local commit on N1 takes place. But we're stuck waiting for that operation to be replicated. Meanwhile, N1 can service reads showing T1 as completed, because T1's already committed locally. So it goes ahead and returns reads of that dirty state. Then N2 says, hey, I haven't heard from my old primary in a while. I'm going to elect myself a leader. So it becomes a leader. and does not have T1. So when it gets back in touch with N1, it says, hey, what are you doing with that write? That's not part of our authoritative history. Get rid of that. So it throws away T1, and we now have an aborted transaction, which was still allowed to be read. Lost updates are even more pernicious. This is a case where you write something, and it's committed successfully, and then it doesn't show up later. This happens when you perform a write to, say, node N1. N1 tries to replicate it out and keeps track of the nodes it's waiting on. It says, I need to hear back from N2 and N3 so that everybody in the cluster knows about this write. But if it doesn't hear from N2 and N3 in a while, it declares them dead, right? It's like, well, I haven't received any letters for 2 years now, so I guess I might as well remarry. It's a different book. So it says, OK, N2 and N3 are down. I'm not going to hear from them again. I am now a cluster of 1. It's just myself. Well, OK, so write 1 is now waiting on exactly nobody, because the cluster's only myself, and I've already committed. So I'm just going to go ahead and return write 1. It's good to go. You're done. Well, then it realizes, wait a minute. I'm only one person, and there used to be 3 of us. I'm not a majority, so I have to shut down to preserve safety. So it promptly kills itself. But not before acknowledging your write, which is lost. Now this occurs because inside of VoltDB is this thing, it's called Zookeeper, but it's not Zookeeper. It's like a Zookeeper alike that they wrote their own consensus algorithm for. And it has this notion of a watch, which lets them subscribe to state updates. And the watches are asynchronous, which means that there's a race condition between the acknowledgement of uncommitted, or acknowledgement of transactions which are waiting for responses, and the shutdown process. So the solution is, once you determine that the cluster has shrunk, you shut down immediately instead of waiting for a watch to do it asynchronously. And that way, you won't get into situations where the cluster is small, and you sign off on those writes, and then shut down later. Unfortunately, it's still lost data. OK, what's up? Turns out that on crash recovery, VoltDB picks the longest log as the authoritative one. Which makes sense, right? Like, imagine that you're all keeping a journal together and you're copying each other's entries, and somebody goes off for a while and you haven't heard from them. They come back with like 200 pages of journal entries. Obviously, they're the furthest ahead. They should be the one that's trusted, right? Well, imagine that N1 is isolated and takes a whole bunch of failed transactions. It journals them all dutifully to its disk, but it can't replicate them. N2 elects itself a primary without those failed transactions and processes, say, a single successful transaction. Now, if these nodes then crash and are restarted, N2 has however many operations were shared plus 1, and 1 has however many operations were shared plus, I don't know, 100 failed transactions. So N1 has the longer log and is considered authoritative. So we preserve all the failed transactions and promote them to successful ones, and throw away the successfully committed transaction on N2. Worst of both worlds. The solution is to reconstruct the cluster state from the fault log. So every time there's a change in cluster membership, you journal that to the failure log as well, and then you try to reconstruct which one was authoritative from that. These are all single partition failures. I also tested multi-partition transactions, and I didn't find any faults. I think this is because the multi-partition initiator fully serializes every update. So there's no chance for you to hit concurrency windows because it's just doing one thing at a time. So VoltDB 6.4, thanks to our collaboration, passes all of its Jepsen tests for strict serializability. This is, I think, the strongest result of any system we've tested so far. I'm really proud of VoltDB for that. In the future, we want to add a formal model for the replication algorithm, because it hasn't been formally described, partial failure testing, and also look into clock skew, because I think there are some places inside of VoltDB that rely on synchronized clocks. Up next, Crate.io. How many people have heard of this one? Pretty small. So Crate, at version 0549 back in August, it claimed to be a distributed SQL database for like Internet of Things data, analytics, that sort of thing. But it makes an interesting choice, and we're going to talk about that choice in a little bit. It claims that after having written a record, the record will be consistent and immediately available when selecting that primary key across the cluster. So it might not be visible in indices, but you should be able to select by primary key and see the most recent copy of that key. The problem is that your application, the beautiful dancer up here dancing on the crate, is in fact on a foundation of Elasticsearch tires, which means it's kind of shaky and wobbly, right? Elasticsearch 1.0 or 1.1.0 had extensive data loss in partitions. 1.5.0 had less extensive data loss in partitions. Crate uses 1.7, so it's not entirely clear whether it's actually going to be broken. Now, Elasticsearch 1.7, unfortunately, offers stale reads, dirty reads, lost. Oh, come on. How bad are dirty reads anyway? Is this actually going to be a problem for us? Well, unfortunately, yes. Because dirty reads affect the safety for Elasticsearch updates. When you update a record in Elasticsearch, and also in Crate, you perform a read of a value, and it gives you a version number. And when you write back, you say, update only if the version number hasn't changed. So I get version 1, I update my copy to version 2, and I write back. And as long as the version's still version 1, v2 will commit. That means that there's two clients, A and B, that both fork version 1 and then try to write back their conflicting copies of version 2. One of them will win, and the other one will fail, because its precondition on the version will not succeed. This is how we force serialized updates. It's the same idea as first committer wins in snapshot isolation. This, of course, implies that versions have to be distinct. But the problem is they're not quite distinct. So we'll do a test where we're going to write a whole bunch of unique integers to a key, and then we'll read it a bunch of times and look at which versions have which values. What we should find if you write 1, 2, 3, 4, 5 is versions like 1, 2, 3, 4, 5. Maybe there'll be a few missing values because some operations could crash. But you should never get into a scenario where one version identifies two distinct values. But unfortunately, we read exactly that. We do a query, and we find that version 2 has both value 1 and value 3. So that's a dirty read. We saw some uncommitted state. But you say, OK, at least it's a read-only anomaly, right? So reads aren't supposed to affect my write safety. Here it gets a little complicated. We're going to write our value on top in black and our version in blue on the bottom. We start off with value 10 at version 1. And a transaction on top tries to add 3. So we read 10, add 3 to get 13, and we write back 13 at version 2. So far, so good. Concurrently, the bottom transaction tries to subtract 2 from the current value. So it reads 10 at 1, subtracts 2, and writes back 8 at 2. And it fails. This transaction does not succeed. However, because dirty reads are allowed, another transaction can read that failed write of 8.2, add 1 to it, and write back 9.3. And its precondition says that its prior version has to be version 2. And in fact, the prior version is 2. It was 13 at 2. But notice that we didn't add 1 to 13. We added 1 to 8. The dirty read state got promoted back into a write because of an update. So look at the operations here. We start with 10, we add 3, we add 1. That should be 14, right? But 10 plus 3 plus 1 is 14, and what we actually got was 9. So that's clearly not right. Even if you include the fail operation, -2, 10 minus 2 is 8, plus 3 plus 1 is 12. That's also not 9. It preserved the garbage update of -2 and lost the successful update of +3. All as a result of a read anomaly. This is why if you do a read, modify, update cycle in any kind of database, you must use read committed. It gets worse, unfortunately. Even if you don't do any updates, even if you just do like plain old inserts without ever changing a value, Crate will lose those too. It's not Crate's fault. It's an Elasticsearch problem. We say, OK, what if we use a newer Elasticsearch? Because Elasticsearch closed the old issue for network partitions causing data loss. It said it's fixed now. On the resiliency page, it says the network partitions causing lost documents, that's fixed in 5.0.0. So I went and tested at 5.0 alpha 5, and in fact, it still offers dirty reads, it still offers lost updates, and it gets into weird states where like replicas will return wildly different results for queries, even hours after performing writes. OK, so bug 2031 is dirty reads. There's no plan to fix this, which means you're not going to be able to do safe updates in Elasticsearch or Crate until that changes. Lost updates is 2384. That's where you can promote stale primaries to real primaries. So it takes an older version of the authoritative record, just, oh, sure, you can be the new leader. There's a partial fix for that in 5.0. A full fix, they say, is scheduled for 6.0. Replica divergence occurs because when you do operations which do not succeed, sometimes they stick around in the replica anyway. But the replicas don't confer to see like whether they should get rid of those updates or apply them. So you get into situations where one replica has a whole bunch of uncommitted documents that you can query for, and the other one doesn't. And it takes until you have another failure for them to reconcile. So that's still unaddressed, at least as of December in 5.02. I recommend, as usual, that you do not use Elasticsearch and, by extension, Crate as a system of record. You don't want to use it as your primary data store. But it's perfectly OK to use it as a secondary data store, a derivative store. So put your data into a Postgres or an S3 or RDS, whatever, and replicate it continuously into Crate or Elasticsearch. And you can take advantage of all the nice things those systems give you. In addition, I want to encourage vendors not to make up their own consensus algorithms, because Elasticsearch has known about these bugs in their replication system for like 3 years now. We keep telling them to use Paxos or Raft or Zab or something, and instead they keep layering on patches, and every time they're still broken. So it's getting better over time, but I'm not necessarily convinced they're going to be able to fix these problems without a fundamental redesign. Now, Crate and Elasticsearch are still well suited for machine data. So if you're doing sensor acquisition, you don't care if 5% of your sensor data is missing. If you're doing search, you generally don't care if a few documents are gone, just so long as they come back eventually. And that's why it's perfectly OK to keep using these systems as derivative stores. Most recent research I want to talk about is from CockroachDB. Cockroach is a really unusual beast. It's a scale-out SQL store, like Crate and like VoltDB, but it speaks the Postgres wire protocol, which makes it a drop-in replacement for some existing applications. It looks a lot like Spanner, which is Google's globally distributed data store for external consistency for linearizability. It uses what are called hybrid logical clocks, which means there's some dependency on wall clocks to ensure correctness. We'll get into that in a bit. Now, Raft is used extensively inside of CockroachDB. So every shard in the key space has its own Raft cluster. And the Raft clusters are linked together in trees. So if a cluster becomes too big, say more than 100 megabytes, it gets split up into two halves. And then the original cluster now stores pointers to the left and right side. So at the root, you've got, like, I don't know, a several hundred wide tree. And then every one of those nodes could itself be its own tree, spanning out to cover very large data spaces. Now, the tricky bit is that Raft only gives us linearizability on a single cluster. So every transaction we do inside of a single shard is going to be linearizable by virtue of going through Raft. But Cockroach cheats a bit. For performance reasons, it doesn't do reads through the Raft state machine. Instead, it keeps what's called a leader lease. So when you elect a leader, it says that leader can service reads without going through consensus by virtue of having been the leader. And its job is to shut down really quickly if it ever loses communication with its secondaries. So long as timeouts work correctly and reliably, this is OK. But that does imply that you're going to need to have reliable timeouts, which means you probably want to be running on physical nodes instead of like maybe like VMware VMs, which could like pause for several minutes and go somewhere else. The other problem is that transactions between Raft clusters go through a custom protocol which uses hybrid logical clocks. This requires clock synchronization to within epsilon seconds. So by default, they say you have to be within 250 milliseconds of each other. If you go outside of that, your transactions could see non-serializable anomalies. So maybe you could read some data from the middle of a transaction or get into other strange update cycle problems. Now, Spanner blocks writes. So every time you do a write in Spanner, you have to wait 7 milliseconds to ensure nobody else is conflicted with you. Writes in CockroachDB commit immediately as soon as they're replicated. However, where Spanner reads are fairly quick, reads on contested keys in CockroachDB might have to block up to the clock skew threshold. So maybe 250 milliseconds, maybe a few seconds. That's how long the maximum blocking time is for a read, if somebody else writes to the key while you're reading it. If nobody changes it, you're good to go and you can return immediately. Now, Cockroach doesn't necessarily offer full linearizability across keys. Single keys are linearizable, but between multiple keys, you only have serializability. And that implies some strange things can happen. In a linearizable system, where we have, say, two transactions that are executed sequentially, like insert comment A and insert comment B. Maybe the first comment is, oh my goodness, there's goats on my roof. And the second comment is, oh, it's fine, they're just mowing the grass for me. Those two comments should be seen in order, right? You don't want to see a reply without the context of the previous comment. Now, one option is that if I do a concurrent read with these two inserts, I see nothing because the select linearizes before the inserts do. Or maybe the select linearizes after A, so I see A alone. Or maybe the select linearizes after B, and I see A then B. But I never see a violation of causal order. I never see B alone without A, if it's linearizable. But CockroachDB is not quite linearizable. It allows this to happen. So you can have a situation where B gets linearized or serialized first, then you do a select and see B, and then A takes effect, even though A happens strictly before B as far as the client is concerned. So they call this a causal reversal. Not linearizable, but still serializable. Now, Cockroach Labs wrote their own test with Jepsen, and they determined a couple things. One of them is that their clock to detector was insufficiently aggressive. The other one is that their SQL timestamps that they choose for transactions have to be derived from the underlying KV store layer. These are fairly minor changes. They came back to me and said, well, we'd like to go deeper. We'd like to understand, are there more things we could find? Can you review our tests for us? And we were able to find a couple of really interesting things. So imagine you have a system of two tables containing a bunch of numbers. And you execute a select statement where you select the biggest number from both tables. So that would be 3. Add 1 to it and insert it back into a random table. So the maximum of these numbers is 3. I'm going to insert a 4. If my system is serializable, and Cockroach is supposed to be serializable, I should get numbers 0, 1, 2, 3, 4, 5, and so on. Exactly 1 for every query I execute, right? I should never see 2 copies of the same number, because that would imply that they had read the same set and then both committed on top of each other. Unfortunately, this is exactly what we find in some cases. You can do a select and see that two queries committed in the same, using the same read predicate or the same set of reads. They were both able to perform inserts, as long as it's separate tables. The reason for this has to do with a structure called the timestamp cache, which is how read conflicts are tracked in Cockroach. Every time you perform a read, the timestamp cache stores the set of keys that your transaction read. And its job is to keep subsequent subsequent transactions from modifying those keys. So if you read something, you don't want anybody else to change it until you're done with it, right? Until you've committed. You're still allowed to change records you read, so it remembers that you're the owner of that key now. But once you've read it, it's supposed to be owned by you until your transaction commits. Unfortunately, if 2 people reach for the timestamp cache at the exact same time, they both win. So, yeah, whoa. So transactions with the same timestamp can just use each other's entries because the only comparison is by timestamp ID, not by transaction ID. That means that you can have 2 transactions that perform the same read set and then perform inserts onto that read set without conflicting. The solution is to clear the transaction ID whenever that happens, which allows reads to proceed, but you couldn't go back and perform the insert later. So this gives us fast commutative read operations, but prevents you from having this kind of read-write conflict on the same predicate. The second issue we found is a little easier to understand. This is where you perform a bunch of sequential inserts. So insert 1, 2, 3, 4. We're going to try every inserted number once, and only once. So we should see, at the end of this, something like 1, 3, 5, 10. There might be some missing numbers if inserts fail, but we're never going to see a double copy of the same number. Except sometimes we do. So you select star at the end of this process, and you get like 0, 1, 2, 3, 4, 5, blah, 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 3. Like, OK, A, why are there 2 copies of 3? I only inserted 1. B, why is it all the way at the end of the table? Like, why wouldn't you get 0, 1, 2, 3, 3, 4? This is strange, yeah? At least I thought it was strange. So the reason for this has to do with the fact that single statement transactions can be executed in a single phase. They don't go through the 2-phase commit. This implies they can be retried easily. So the client performs an insert. The server relays that insert. There's like a coordinating server that is going to fan out the transaction to the appropriate replicas. It sends that to a destination server, which commits. But that server maybe fails to acknowledge the commit because of a network partition. So the coordinating server times out on its request and says, well, I'm just going to retry that. So it sends the same transaction again to the original server. That server then responds with, hey, that timestamp you gave me on that transaction, that's super old. We've moved on. That is so 2006. So it rejects the transaction, and the server says, well, I know the answer for that. I'm just going to generate a new timestamp and try it again. So it generates a fresh timestamp, tries it again, it commits safely, and now we have 2 copies of the same insert. But it's going to take a lot longer for the second one to show up because it has to wait for the network to heal, and that's why they show up at the end of the test and not in the middle. So the solution to this is to distinguish between retriable and non-retriable errors. And this is a problem I see a lot of distributed systems clients making. You often assume that an exception or a timeout or a crash implies the operation didn't happen. But what it really means is indeterminacy. It may have happened, but maybe it didn't. And you have to allow both classes of errors. So now there's an ambiguous result type inside of CockroachDB which prevents that double enqueue from occurring. As a result of this collaboration, CockroachDB now passes a test suite. So it offers a fully serializable database so long as, again, clock skew stays within bounds. I think this is great because the world needs more serializable SQL databases. It turned out to be really hard to scale single node traditional databases or do sharding and stuff. The more of these systems that make replication and scale out easier, the better, I think. But this comes with a weird caveat. Your clocks have to be synchronized. So keep that in mind. Google, with TrueTime, claims they can get their clock epsilon down to like 7 milliseconds. I've seen deltas of like multiple seconds on EC2, so if you're deploying in the cloud, like be advised to jack that up. A lot of the big like colo facilities I talk to say they see errors of around 100 milliseconds. So that's 250 milliseconds is probably a reasonable estimate for data center environments. The other thing to be aware of is that this is still beta software. I don't think they've hit GA yet, so performance is still going to be a little bit slow. They're working on it. To recap our wild adventures, when you choose a database, whether you're paying for it and signing a legal contract, or even if you're just installing one from the web, you're locking yourself into that database's behavior, which means you need to read the documentation really carefully to understand exactly what the vendor, here represented by Ursula the Sea Witch, is giving you. It may turn out that you as a systems administrator have to kiss the prince by the 3rd day or your data will be lost. So read the docs very carefully. And then ignore the docs and test it for yourself because they're often wrong. Look out for words like strict consistency, acid, strong consistency. These are weasel words which are used to confuse you and bamboozle you into accepting the product as good when it might not be. They're okay to use in context, right? But like, look for a formal descriptor like serializable or snapshot isolation. I want to encourage both vendors and users to be formal and specific in the guarantees and the invariants they need. Figure out the invariants that you actually do need, because it's going to vary from service to service. For something like a social network, you may only need eventual consistency, maybe not even guaranteed rights for very large data sets like photo posts. If a comment on Facebook goes missing, it's not the end of the world, so long as the ratio is relatively small. However, user registration, you definitely want to be safe. Once somebody's taken a username, you don't want to hand it out to anybody else. Consider the failure modes in your system. So don't just test in a happy case, but test with process crashes. Use kill-9 to simulate the crash of a process. Simulate node failures by terminating AWS nodes or flipping the power switch. Use clock skew. This is a really easy way to make systems fall over. Set the date. Or use libfaketime to insert an LD preload shim that will lie about the date to the standard library. You can use garbage collection IO pauses as your tools of destruction as well. So use sigstop and sigcontinue to simulate a process hiccuping for some time. And you can simulate network partitions with iptables-jdrop and probabilistic loss of packets with TC. I want to advocate for testing your systems end-to-end. So don't just reason about the individual database, but also think about the composition of the database with the services above it. So in addition to testing Postgres, test Does my Rails application making queries to Postgres enforce transactional boundaries correctly? Did I choose the right isolation levels in order to guarantee that, say, users can only be registered once, or I can only post one cute cat picture per day? Finally, as Tolstoy reminds us, if you look for perfection, you will never be content. Understand the databases are very difficult to make correctly, and all these vendors are doing the best they can to solve complex problems with limited resources. It's okay for us not to be perfect, but I do want to encourage people to do a bit of basic testing to try and improve their software, at least to a baseline modicum of correctness. This means engaging in property-based testing. So not just, is 1 + 1 2, but can I add any two numbers together? Generate randomized operations and apply them to your system, and then verify high-level invariants, like can I register users? Can I upload photos? Can I make comments on a post and order? And test them in the presence of distributed systems failure modes so you understand how the system is likely to behave at scale where those failure modes are exceptionally common. This work is funded by VoltDB, Crate.io, and Cockroach Labs, respectively. And I also want to thank Boaz Leskis from the Elasticsearch team and Peter Alvaro, a researcher at UC Santa Cruz, for their invaluable assistance. Thanks to all of you for coming. If you want to see more about this research, you can go to Jepsen.io. And I want to thank you all for your time.
Hi, thanks for a wonderful talk. I wanted to ask you for your opinion on the more recent database development, some of which bases on presence of atomic clocks in servers, such as F1 database by Google. Mm-hmm. Do you think that's the way forward, or do you think we should continue working with the hardware that we already have?
Okay, so things like F1 and Spanner are a significant advancement. In particular, they allow you to do efficient queries between multiple Paxos groups or multiple Raft groups quickly. But remember, it's still Paxos and Raft under the hood, so you're still paying that minimum two network hop latency cost for every operation. That means that it's not a panacea, but it's still helpful. And I think that to whatever extent we can deploy this hardware, it's going to help us. That hardware is still not there yet. Google Cloud, I think, is talking about bringing in true time as like an API call soon. So for the meantime, it probably makes sense not to be too concerned with it. But for people like Cockroach, right, are betting that this is going to become a norm as we go on. And I wouldn't be surprised if we do see high-resolution clocks in the future.
You also revisited Mongo back in February.
Uh-huh.
And you don't talk about that here. Can you tell us a little bit about the tests that passed and the caveats you left behind in that report?
Yes, so I also retested MongoDB, which is not in this talk because I'm talking about that on Monday. And so MongoDB, in fact, had more serious issues than I realized. There was a fundamental problem in its replication algorithm which could cause it to lose acknowledged writes. The reason for that has to do with an assumption of synchronized clocks. They use the wall clocks to determine which replicas are most recent, and that's not safe. So we were able to induce data loss with a combination of network partitions and clock skew in a certain pattern. And that was fairly easy to reproduce, but it required that I understand how the algorithm worked in order to see it. I couldn't hit it with random partitions. They've since patched that. Their new replication algorithm they've been working on for the last 2 years now, I think, appears to address that problem. We found a minor issue in it, but it does pass all of its Jepsen tests now. So I think it's also a really good result for MongoDB. Yeah.
For things like relying on wall clock for most recent, how often do you find things actually within source as opposed to instrumenting from the outside?
I do relatively little reading of source code, mostly because database source is large and scary. So most of what I find is just from the outside. In some cases, like VoltDB, the instant I poked at it, it fell over, and it's like, oh, well, there we go. In cases like Mongo, I actually had a really long discussion with the engineers, and we started sussing out, here's where we think it could fail, and that helped me design a test specifically to exploit that failure mode. So I think it's better if you can talk to the engineers and read the code, but it's not necessarily required in all cases.
Hi there. I was wondering, has anyone sued you yet? Sort of the behind the question is, database vendors are notorious for refusing to allow their customers to talk about their database. Mm-hmm. So I see you as a force for good for the public, but I won't. There must be some intermediate waffling going on.
Yeah, some of the companies which pay me have also tried to get me fired. So I don't know. It's a wonderful world. I'm really happy that this is happening, but so far nobody has sued me. Sometimes they're upset, but we generally are able to talk it through and come to a productive discussion.
So in which context are you developing this? You are a contractor and you're working for database companies, and that's how you finance this and run this? And
Yeah, originally this was a nights and weekends project, and now I do it full time, so I have my own consultancy, independent.
nice, cool.
So you talked a lot about NoSQL stores and some of the newer SQL offerings that have come down the pipe. Is there any desire to extend this research into things like block stores and even kind of the more traditional like NFS or Gluster or something like that?
Yeah, we could totally do file systems. Actually, I can't talk about upcoming clients, but yes, more of that will happen. And in fact, it's not just for distributed systems too. You can use this Jepsen infrastructure to test local systems or in-memory structures. One of the things that I've been building the last few weeks is like a testing tool where you can write your own linearizable key value store whose network is JSON messages that you print and read from standard in, standard out. And it will apply all the Jepsen testing stuff and simulate a network internally to help you build the system correctly. So there's lots of directions you could take this research. Yeah.
Hey, great talk. What was it? Looking at cases of databases with like kind of narrow scopes, I'm looking at something like a central store of truth. So in these cases where it's kind of a little bit more narrowed, what do you find is kind of working for these narrower scopes, and then for maybe say a case of services that might help to apply a better clock where you're not having to rely on a you're not having to bet the farm on one database. You can like rely on a clock of another service to help generate the ID or the sequence of events, so then you can apply it to something that's stronger for good consistency between applying it on the central store of truth. Can you thoughts on that?
Yes, you can combine multiple systems to build strong consistency properties on top of a weaker storage system. Is that what you're thinking of?
Yeah, exactly.
Yeah.
So in that case, for storage, for central stores of truth, any databases that kind of stand out in your terms for doing that?
Anything that would give you a linearizable or at least sequentially consistent storage system will be suitable as an index. For a really good talk on this, see Rich Hickey's Datomic, D-A-T-O-M-I-C. You can come see me after too.
Yeah, sure.
But he discusses ways that you can build a sequentially consistent data store and an eventually consistent, like large sort of block store, and combine them to get a database.
Okay, perfect. Thanks.
I think that wraps that up.
Okay.
Thank you so much, Kyle.
Thank you. I have one last gift for you all. I would like to invite you to consider, of course, remember to rate the talk. Thank you for coming to Scala Days. And I would like you to consider this wonderful koan in which a value x being a long and a value y being a float can allow x minus x to be -3. Thank you.